Welcome to our solutions for assignment 5.8. Here we're having fun with the definition of integral. The definition as an infinite Riemann sum. So we're going to add up an infinite number of rectangles, and again we're using a regular partition, so our delta x value are all going to be equal. So if we do an infinite number of them, then they are forced to have a delta x that will limit down to 0. So that's an important part of this method. If we do an infinite Riemann sum, we have to make sure that the delta x value, the rectangle width, is getting closer and closer to 0. So our first steps are to set up our definition. We have to think what we're going to use for our delta x. So here our b value and our a value give us the width of the integral or interval. So we're going from -1. Let me subtract in the other order. That would give me an odd order. Let's subtract 5 minus a -1, and we are going to eventually let n go to infinity. So remember, we're going to leave n as a variable until we get to the end of the problem. So this is the width of each of our rectangles, and then we need to find the height at x sub I. So first we have to think what we're going to use as the right-hand side of each, or the right-hand x coordinate of each of these rectangles. So in this case, our a value starts at -1, and we just figured out what our delta x is going to be, 6 over n. So here for the x sub I coordinate, I'm going to just reverse this and make it 6 over ni. So this is the coordinate, and remember that f of x sub I is the height of each of those Riemann rectangles. So x sub I is just the x coordinate that we need to plug into our function. So remember, we're going to have to plug it into the 3x here. All right, so now we've got set up what we need. Now we can do the definition of integral, of a definite integral. So we are going to be finding exact value because we are going to do an infinite number of Riemann rectangles. So our sigma is going to go from 1 to n, and the limit operator is going to make sure that we're doing an infinite number of rectangles. So as we did with any Riemann sum, we are adding the areas of rectangles, so we're taking the height, that is our f of x sub I term, and we're going to multiply by the base of each rectangle, and that's going to be our delta x value. And we're doing a regular partition, so the delta x we just determined a minute ago was always 6 over n, and now our f of x sub I, we're going to take this expression and we're going to plug it into our 1 plus 3 times x. So this is our f at x sub I. This is the height of each rectangle, f at x sub I. All right, now we're done with our calculus. Now it's all just cleaning up that algebra. So let's do some distributive property and combine some like terms. So you could do this perhaps in fewer steps. I'm going to distribute the 3 first. So I'll have a 1 plus a -3 plus an 18 over ni, and then we're still going to have to distribute times 6 over n. So these two terms, I think you see I could have written -2 right away. So in my next step, sigma I going from 1 to n. So in my next step, I'm going to take this term as a -2 and multiply it times the 6 over n. And I'm going to take the 18 over ni and multiply it. So 18 times 6 sounds like a 108 over n squared times an I. And now remember what our next step was. We have theorems that tell us that sigma of a sum is the sum of two sigmas, And we have a limit law that tells us that the limit of a sum is the sum of the limits. So at this point, we're going to split this up. And just to remind you what this was going to look like, we're going to take some terms out of each of the sigmas. So we set it up this way just to give you the idea that we're doing something pretty simple here. But the only thing that we need to leave inside the sigma operator is only changing the value of x. So on this term, on this part, every term is going to have a negative 12 in it. So we could factor that negative 12 out of the sigma. And every term is going to have an n in it. So we could factor that out of the sigma. So the problem is, what's left? If we factor everything out, there's still a 1 left here. So remember that we could put a times 1 right here. When you factor, you're dividing. So we need to put a 1 left over there. In our second term, every term is going to have a 108. So we could bring that out of the sigma. And every term is going to have an n squared in the denominator. But the I term is going to be different. First I will be 1, and then I will be 2, and then I will be 3. So, oops, I wrote 1 there, and that should be I. There will still be this I left in the sigma. All right, and this is where we used our sum formulas. This, we have a theorem we talked about in class. Every term is 1. So the first term is 1, the second term is 1, the third term is 1. So how many are we adding up here? We are adding n times 1. So that is just going to become an n. So we are using our sigma theorems. So this negative 12 over n is still here. And of course we'll cancel in the next step, but let's proceed. And in this sigma, here we have a formula where we know this is the sum of terms will be 1 plus 2 plus 3 all the way up to n. And we know our formula for the sum of the first powers. This will become our formula n times n plus 1 all divided by 2. And of course this 108 over n squared will still be out in front. So we're getting there. Now we just have to clean this up, and of course those n's will cancel. And over here what we're going to do is swap these denominators. So in the first term, and I could do this limit right away, but I'll leave it to do both limits at the same time. So you might do your steps in a different order. That would be perfectly fine. All that's left here is the negative 12. And then this limit as n goes to infinity. So I'm going to swap these two denominators. So I'm going to move the 2 there. And this numerator I'm going to write as n squared plus n. And I'm going to move the n squared below it. So now we have a binomial divided by a monomial. So now you know how we're going to do those limits here. So, and I'll save this yet for one more step to talk about the limits. You could, by the way, long ago have moved this constant of 108 out in front of the limit, but the n would have had to have stayed inside the limit. So I thought it was just as easy to keep those terms there, but that's really up to you. So this square bracket now, when I divide n squared by n squared, and n divided by n squared will be a 1 over n. And remember then, now we're ready to do our limits as n goes to infinity, but there is no n term here. So the limit operator does nothing, it stays as negative 12. And what happens here when n goes to infinity? This fraction, when the denominator gets huge, that fraction goes to 0. So all we have left is the 54 times the 1. So this term is a 54. So I hope our answer is 42, if we didn't make any algebra or arithmetic errors. All right, now let's approximate that integral using a finite Riemann sum, and here you're asked to use L6. Well, we kind of like that dividing it into 6 because our b minus a, the width of our interval, is 6. So this is being very friendly to us, this problem. So we would have a delta x of 1. If, again, we make every delta x equal to each other, then it's called a regular partition. All right, so this is not going to be exactly the value of the integral. So we're not using the definition. This time we are approximating by using L6. We're doing 6 left-hand rectangles. So delta x is the base of each rectangle, and we just decided that would be a 1. And then we have to multiply by the height of each of the 6 rectangles, and those are all different. So think how we're going to partition this. We're going to start at -1. So the left-hand height would be f of -1, and then we're jumping over delta x. So the left-hand edge would be at f of 0, and then f of 1. And let's see if I can make this fit. F of 2, f of 3, and f of 4. How come we're not going to f of 5? Because we're on the left-hand side. So that last partition, that last rectangle, goes from 4 over to 5. But we're measuring the height on the left-hand side. Okay? All right, so let's do some arithmetic here. You could grab your calculator otherwise, but our function is pretty simple here. Our f of x function is 1 plus 3x. So I think I can do this arithmetic. So f of -1 would be a -2. F of 0 would be a 1. Or I'm sorry, would be a 1. F of 1 would be a 4. F of 2 would be 7, f of 3 would be 10, and f of 4 would be 13. And if we do some arithmetic there, it looks like we have 1 times 33. So our approximation for our integral is 33. So definitely not too good an estimate because we know our correct answer turned out to be 42. All right, now let's find the exact area using the fundamental theorem of calculus. So remember the fundamental theorem, we're just learning this. The fundamental theorem says that we take the antiderivative evaluated from a to b. So we take capital F of b minus capital F of a. So a significant shortcut here. So -1 to 5. Of 1 plus 3x dx, an antiderivative of the first term is x, and an antiderivative of 3x, remember how we reverse the power rule. We raise the exponent to a 2, and we divide by it, and then we want to evaluate from -1 to 5. So we're going to put 5 into this value. So we'll have 5 plus 75 halves. And then we subtract, putting -1 in. We'll have a -1, square the -1. This will still be a positive 3 halves. So often the fractions will work nicely when we put those together. So we'll have a 72 halves or a 36. That was 72 because that negative sign distributed. And then we would have a positive 1. So I am happy to report that I got 42. Because remember, this is the exact answer for the integral, and we've already done the definition method, and we knew the answer was going to be 42. All right, our next question is written in a little different format. Hopefully now you can see that this is a Riemann sum, and it tells us that we're going to do 3 equal subintervals. So we're doing 3 rectangles, and we're measuring them at the right endpoint of each interval. So our function, so we are approximating the area from 0 to 1 of 2 to the 6x dx. And now we're doing a finite Riemann sum, so we're going to just do 3 equal rectangles. So I guess I should stop and find my delta x value. Our b minus a, we're going from 0 to 1, and we're dividing it into 3 rectangles. So our delta x for our base is 1/3, and then we need to multiply times the heights of each of the rectangles. So we're not doing an infinite sigma here, we're just doing 3 rectangles, and we're starting at 0, so our first right-hand endpoint would be at f of 1/3, and then the right-hand edge of the second would be, the height would be f of 2/3, and then we jump to the edge here, and the next one will be at our end of f of 3/3, of course that's f of 1. And now we can find f of 1/3, so we're evaluating, this is 2 to the 6/3, so 2 to the 2nd power, in other words, will be a 4. And then we're doing f of 2/3, so that would be 2 to the 12/3 when I multiply the exponent by 6, so 2 to the 4th. We'll have a 16, and then we'll have 2 to the 6 times 1, so 2 to the 6th, and 2 to the 6th will be 64. So 16 and 64 add up to 80, and then we'll have an 84. So I think 84/3 should be our approximation of the area under that curve. All right, and our next question, let me pause and find it. So we are given a Riemann sum, and notice it is an infinite number of rectangles. So this is our height here, our f of x sub I, and the delta x sub I would be the base, so this is our height, and the delta x sub I represents the base, so it's pretty straightforward. Oops, sorry for jumping around there. And our interval goes from 2 to 6, so a lot of what we need here is already given. So now we only have to figure out what our function looks like. Well, it's pretty straightforward, isn't it? If this is our f of x sub I term, then we must know what our function is. Our function must have an x, and our function must have a I've skipped the ln here. Must have a natural log of 1 plus x squared, because we simply put x sub I into our function. That didn't highlight very nicely. Let me try highlighting that again. Our x sub I term, this is our f of x sub I, so we're simply putting x sub I into these x variables. So we're simply working backwards here. And delta x, remember, in our integral is represented by the symbol dx. So we're simply taking the Riemann sum symbols and working backwards to integral symbols. All right, and let me find one more problem for us. Can we work backwards from this sigma notation and find out what integral it is? So again, we know this is the definition of an integral because it looks like we're adding up an infinite number of rectangles. So how can we make this look more like a height times a base? Well, let's see if we can pull this apart. And to give you a clue here, this should be I going from 1 to n. How about if we turn this around or split this up here? And what if we made this an I to the 4th over an n to the 4th times a 1 over n? Now, why would I do that? Because remember, what I want this to be is an f of x sub I times a delta x. So I would like this. This makes much more sense to me here if these two things match. So let's think what we know then if this is going to work. then we're thinking our delta x, which is our formula b minus a over n, is equal to 1 over n. So remember that that tells us that the distance from a to b. It doesn't tell us where we're starting, but it tells us the distance from a to b, the distance between our limits, is equal to a 1. And then let's take this I over 4 over n over 4, and what we think that this should be then is our f of x sub I. So what do we think we might be doing here? So remember what x sub I is. We're kind of taking this apart. Our x sub I formula was a plus I delta x's. Well, our delta x, we just came up with an idea that our delta x, value was 1 over n. So our a value here must be a 0. There isn't one. So what would be f of x sub I? If x sub I is I over n, what are we doing to it? It looks like f of x must be taking the value to the 4th power. So let's see now. We kind of did some trial and error. We now think that a is 0. So that's our lower limit. And we knew that the distance between b and a, up here we knew that b minus a was going to be 1. So if a is 0, then b is 1. We think our function is x to the 4th dx, and that value is equivalent to the Riemann sum that we were given to start with. So you can go backwards and you can go forward.